okay, we're going to take a shot at these, but every time you do one of these questions, it's very smart to go back up here and say, what was the chapter about? It's about understanding the relationship between an exponent and a log, and it's about understanding certain log rules. So they cover 3 here, which is hard to understand and hard to explain. So sometimes it's good to just memorize it. But this is essentially saying a to the 0 is going to be 1. That's true for anything with the exponent of 0. It doesn't matter what the base is. That's the base where a is. And then this is a with the result is equal to x, but you can see that here that a is to the x, and here all it's saying is what do we put over this little a to equal a to the x, and it's easier with numbers, right? So if you were to look at that in numbers, here's your homework. It's always easier when you use numbers, right? Instead of what they're using letters. So the first one is saying any number. You can put any number in for a. 2, 1. What do I put as an exponent over 2 to make 1? The answer is 0. And that doesn't matter what the number is here. That's why they're expressing it generically. Then the next one, it looks weird. It's saying when I have, instead of a, I'll put a 2. And then they're saying big A, so in this case, these two things match, right? And then they're saying it to the 7. And when we're saying it equals the 7, this is pretty, see these X's match. See these X's match. These numbers here match. So when these two numbers match and these two numbers match, the answer is whatever that is. So the point of this is asking, what do I put, if I put 7 over this, if I put this over an exponent of this, what does it equal? Well, it equals obviously 2 to the power 7. It looks like a stupid rule, right? But this can be expressed differently. For instance, if I had 3 here, and I know 3 and 9 is pretty simple. It's quite clear the answer is 2. But you can see that 9 here can be expressed as 3 to the 2. So when I can make this number here match this number, I get my answer right there. 2. Now you might say, well, it's obvious for 9, but obviously I would be choosing something different, like when I have 225 and the thing up there is squared. Is that? Well, that's hard to see unless you realize, oh, that square root of that is 225. And therefore I can rewrite it as that. And therefore the answer, because I've made these match, the answer is quite clear. It's this. So that's what they're teaching. The next one is very hard and takes some proof. So I'm not going to bother going through it. But I would suggest you memorize the rule log, the logs of the various log rules. And one of them, all you have to say is rules of logs. And you get right there. And that's all the rules. And that's the last one they're saying. It's kind of confusing. It's essentially when you put this thing as an exponent over b, the answer is the value where k is. But you have to do some examples to really understand that. The rest of these are straightforward. This one says I can move the exponent in front. This one says when I have the same base being subtracted, I can instead write the numbers m and n divided. This says when it's added, I can instead multiply m and m. And it goes both ways. You can go either direction. And this is the rules you've been covering lately. So it always helps to go and say, okay, what are some of the examples they've given and why, right? And how do I figure it out? And it takes some time to understand this. So that's why they walk you through it slowly. Well, let's just jump right to it. I'm going to do a different page so I don't step on those. Okay. This just wants you to change the exponent form to the log form. And let me make it easy for you. Identify the base, 4. And that means it'll be log base 4. Identify the answer, the result, 16. That means the 16 goes here. And I forget what this thing calls it. It has a name. I guess exponent. Identify the exponent. It goes here as the result. It's the new result. So this says 4 squared is 16. So whenever we have it like this, it's asking, what do I put over 4 to get 16? As an exponent, the answer is 2. 4 times 4 is 16. Practice your exponents if you're weak. So we can do them all like that. Here's 3 as the base. I could just put it where the base is. 81 is my result, so I can just put it where the 16 is. And 4 is the answer I'm looking for. I'll just write it 4. which means 3 to the power 4 is 81. That's 3 times 3 times 3 times 3. That's 3 to the power 4. That's what 3 to the power 4 means. It means 3 times itself 4 times. This, we would just do it the same thing. So the base is 8. The result is 1. What do I put over the power of 8 to get 1? 0. This one's getting a little trickier, though. But we can still use the same rules. The base is 6. The result is 136. And therefore, the exponent that would have to put over 6 to get that is negative 2. So 6 to the power of negative 2 is the same as 1 over 6 squared, which is the same as 1 over 36. So the answer to this is negative 2. So no matter what, there's the base. 1/3. There's the result, 1/27. What do I put as an exponent over 1/3 to get 1/27? 3. Right there. That means 1/3 times 1/3 times 1/3, that's 1/3 cubed, is going to be 1/27. Practice your fractions. This is the same thing. Log base 8. The result is 2. What do I put over 8 to get 2? You might say, what? What's a third? Well, remember that 8 to the third. Remember this rule. You have to memorize your exponent rules. This is the power. This is the root, which means the cube root of 8. It's the same as writing this like this with a cube. Well, what number times itself 3 times will make 8? That's what a cube root is. 2. 2 times 2 times 2. So 2 times itself 3 times is 8. The cube root of 8, instead of square root, is 3. Cube roots are hard to memorize. So what you can do is say, well, what's 3 times 3 times 3 times 3? 27. That means the cube root of 27 is 3. What's 4 times 4 times 4? 64, which means the cube root of 64 is 4. What's 5 times 5 times 5? 125, which means the cube root of 125 is 5. You can do it like that. And so they're asking you to go from log or from exponent to log. So of course the next question they're going to ask you to do is to go from log to exponent. Same rules, just reversed. Find the base. The base in the first one here is 2. So 2 to the exponent of 3 will equal the result. The result is always here in the log. 8. 3 to the exponent of 4 will equal 81. 5 to the power of negative 2 is the same as 1 over 5 squared, which is the same as 1 over 25. So we would write it as 5 to the negative 2 is equal to the result, 1 over 25. Here's the base, 1/6. So 1/6 to the power of negative 3 is equal to 216. Now you might say, well, I don't get that one. Okay. Well, 1/6, this is a rule of exponents to the power of negative 3. Means I can apply that to both numbers individually because they're divided. Well, 1 to the negative 3 is just sending the 1 down here and becoming 1 again, so you can just ignore it. But this, when the negative 3 is on top of the 6, we used to send the negatives down to the denominator. But this one's on the denominator, so we send it up to the numerator. So it becomes 6 to the power of 3 times 1 here, which doesn't matter. It just essentially comes up. And 6 to the power of 3 is 216. So that means 1/6 to the power of negative 3 is equal to 216. So written like that, it would be written like this. 1/6 to the power of negative 3, just try to draw 3 better than that, is equal to 216. And then these last two, 6 to the power of 1/2 is equal to the square root of 6. And that's true. 1/2 power just means square root. That means that's the root. So square root of 6. And then here it's saying 10 to the power of 0 is going to equal the result of 1. So it's just reverse. Why are they giving this? So you can understand the connections between log and exponents and not get flustered, because everybody gets flustered when they see a log. They get all freaked out. Log is just a number. It's just something we write instead of writing the actual number because we don't want to write so many decimals. They're asking you to evaluate. So what this is asking is the base is 5. They're asking me, what do I put as a power over 5 to equal 5? Well, it's clear the power must be 1. So the answer is 1. B, what do I put to the power of 7 to equal 1? Well, you have to know your exponent rules for that. Anything to the power of 0, everything to the power of 0 is 1. X to the power of 0 is 1. Even when you don't know x. Okay. This one's asking 7 to the power of what is going to be equal to the square root of 7. Well, here's where you have to remember your exponent rules. The first number up top is the numerator is the power, but the bottom number here is the root. So a half exponent is the same as saying square root of 7. And then here, what do I put as a power over 3, at 2/3 rather, to equal 8/27? Well, whatever power here will get applied to both numbers. So you can just put it here. It's quite easy to see that from the 2, that 2/3 is 8. And then you realize, oh, well, 3 to the third is 8 is 27. So that means the exponent that's out here must be 3. And it gets applied to each thing individually. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Then the last one is a little tricky. What do I put over a power of 2 to get something that says a cube root of 2? Well, just like a half would be a square root, a third is a cube root. So the power would be 1/3. Be aware, if they had another exponent here, like 5, out here, that's a power. Then the exponent I would write here is 5/3. If they had a cube root here and a power here, or even the power here with the 2 and the cube root outside, that's 5/3. That's saying take the 5th power of 2, 2 times 2 times 2 times 2 times 2, and then cube root it. It won't be a nice number. It'll have a lot of decimals. That's why we learn to write it like this. What the hell's the point of logarithms? Logarithms measure things that are so huge that numbers don't help. For instance, when we look at magnitudes of earthquakes, I forget what the actual measurement, it's some sort of amount of force. But for instance, 100, whatever the unit force is for earthquakes, I forget, would be described as 2, a class 2 earthquake. And that's because 10 to the power of 2 is 100. Now let's say you get an earthquake that's 10 times harder, 10 times stronger. It's 1,000, does much more damage. 10 times the force is much more. That would be classified as a earthquake category 3. In other words, it's 10 to the power 3 is equal to 1,000. Get used to the power over 10 equaling the number of zeros here. Okay, so what about a magnitude 7 earthquake? How much more stronger than a magnitude 2 is? Well, 2 would have 2 zeros, and a 7 would have 7 zeros. 7 has 5 times more zeros, so that means an earthquake 10 to the power 7 is 5 times. Sorry, 5 zeros, 10,000 times. 10,000 times the 5 zeros, 100,000 times more powerful than a class 2 earthquake. That's why we use the 2 to 7. It's saying, well, that's 10,000, that's 100,000 more stronger than that. But I don't want to say the word 1 million or 10 million. I just want to say 7. Okay, let's keep going. So for things so large or so small, you don't want to use simple numbers with them. Okay. 4, I think you have 4. Yeah, 1 to 4. You don't have the other ones, which is too bad because the other ones are important. Solve for x. So when you don't see a number by log, it's assumed to be a base 10. So write a 10 under as a base for all of these. When you don't see a number, it's base 10. And by the way, when you see the word ln just means log to the base of a number called e. We'll get to that. E is a very magical number like pi. But ln is just it's called natural log. It's log base e, if you see ln. Okay, well, if these are all base 10, then it's asking me What do I put as x? Because they give me x as the answer each time. See, well, sometimes they don't. Sometimes they give me the actual answer. What do I put to the power of x to equal to 1/10? That's A. Well, it's clear that this 10 went down here somehow and only has the power of 1 down here. So x is -1. B. What do I put as a power of 10 to equal 1? Well, the only possible answer is 0. C. What do I put as a power of 10 to equal 1,000,000? Well, count the zeros. How many zeros do you see there? 6. Power 10 to the power 6. So that's the nice thing about 10 powers. It's how many zeros here. Even the negative is interesting. -6 is this. There's 1 decimal place, 2 decimal places, 3, 4, 5, and then the 6. You might say, wow, Pete, but there's only 5 zeros. Well, if you want to put this one in there, now you need to realize there's 6. But really the 6 decimal places are 1, 2, 3, 4, 5, 6. So it was at 1 and it went 6 to the left. That's what the negative means. So you can still use the system, especially if you put a 0 here before the decimal. So if I see -6, put a 0 here and 5 after the decimal and then the 1. So going back to that, 10 to the power 6 though is 1,000,000. Then over here it says, this is an interesting one. What do I put as 10 to the power to equal 25? Well, 10 does not equal 25, does it? At all. So we have to stretch our brain a little bit and say, okay, how can I get 25? Well, 25 squared might be possible. No, it's not going to happen. How can I get 25? Now there's a way of doing this because they've given you, to get 25, is they've given you it says round your answers to 2. I guess we're supposed to use a calculator. So since they've given us the whole thing, you can just take your calculator in 25 and hit log. And there you go. And since 2 decimals, it would be 1.4. So here's 3 decimals. Right? This is the answer. But they want 2, so this 7 makes the 9 go up to 10, and that 10 makes the 3 go up to 4. So that's to 2 decimals. This one asks, what do I put over 10 to get 0.25? Oh, sorry. What is 10 to the power of 0.25? Well, if you want to really be tricky, that's a quarter. 0.25 is a quarter. So they're asking me to take the 4th root of 10. But your calculator can still handle 10 to the power of 0.25. It's 1.778, so it rounds out to 1.78. Be aware that I could have also done what I said. I can find the 4 root of 10 by hitting second function, x to the x, and ask it to find the 4 root, and hit equals. And I get the same answer. Okay, so in these two, they want you to do calculators, and this one too. They're saying this one's a little easier. Just like 10 to the power of 2, they're saying 10 to the -2 is equal to my answer. What's my answer? Well, if this said 2 instead of -2, it'd be 100. But it said -2. So how many zeros are that? We put 1 here, 1 more here. There's my 2 zeros, and my 1. That is 10 to the -2. Your next questions are skipping past 4, which is too bad because I think 5 and 6 are incredibly important. Well, they give you 6. So what they're skipping here is 5, which is asking you how to use your log. Or this, I really wish they hadn't skipped this because these are really important. I'm going to give you 1 to show you how important it is. These ones you actually don't do with a calculator. You have to figure out the connection between this and this. And you might say, Peter, there's no connection between 3 and 81. Like, what do I put over 3 to get 81? But there is. 3 to the power of 3 is 27. 3 to the power of 4 is 81. So if you know that 81 can be converted to the same base, 3, right, to 4, you now have your answer right there. 4 here, squared is 16, to the power of 3 is 64. So this answer is 3. This answer is 4. 4 plus 3 is 7. You might say, how do I get that? Well, we put 5 to a third to get a cube root of 5. So the answer is a third. What power do I put over 5 to get 125? 3. What power do I put over 5 to get 25? 2. 3 minus 2 is 1. What do I put over 2 to get 4? Negative 2. What do I put over 3 to get 1? 0. Minus 2 minus 0 is minus 2. So they're useful. They're useful because you stretch your brain, and these things require brain stretching, because nobody intuitively can think of a log in their head and understand what's going on. Well, you can if you spend all day with logs. Use your knowledge of logarithms to solve this. Okay. This is asking 5 to the power of 3 is going to be equal to x. Well, 5 times 5 times 5 is 125. This one here is asking, I'm going to do that. Ooh. This one here is asking x to the power of 3 is going to be equal to 27. What is x? Well, we can solve this by figuring out what number to the power of 3 would be equal to 27. 3 times 3 is 9, times 3 is 27. So it's clear if I write 27 like this, that the x over here must be 3. Here on C, they're saying, what do I put over the power of 4 to equal 164? Well, it's got to go down there somewhere. Squared would be 16, but to the power of 3 is 64. So that means 4 to the negative 3. This says, what do I put as a power of 4? Sorry, what's the power of 4 to the negative 2? Well, the negative 2 applies to the 1, which is just the 1, and to the 4 in the denominator. Well, it's a negative exponent, negative 2 on that 4. So it sends the 4 to the numerator, and that exponent of 2 becomes positive 2. 4 to the positive 2 is 16. So my x is 16. You can always use your calculator too. This says, what's 5 to the power of a half? They don't want the real answer. It's just the square root of 5. This says 4 to the 1.5 is equal to x. But keep in mind, 1.5 is the same as 3 divided by 2. This is a square root. What's the square root of 4? 2. 2 to the power of 3? 8. So that means 4 to the power of 1.5 is 8. This could be proven by taking 4 to the power of 1.5. 8. But you can see 8 is the same. 1.5 is 3 divided by 2. I could just do 4 to the power of 3, which is 64, and take the square root, which is 8. Or I can do the square root of 4, which is 2, and then take the power of 3, which is 8. Stretch your brain.